Over the past half-century, semiconductor technology has become an integral part of our daily lives. This has occurred primarily because we have learned how to make devices smaller and smaller and thinner. And as we make them even smaller and even thinner, we can envision that in the future, most things that human beings use, the clothes that we wear, the tools that we use, the buildings that we live in, will be smart. They will be embedded with logic, sensors, and generate their own energy. This poses a very important question. What happens to the properties of these materials once you thin them down to the physical limit, the smallest scale you can achieve, to a thickness of a single atom? This is the major focus of my research group. We take technologically important materials, develop methods to synthesize single atom thick derivatives of them, and understand how their properties change. What we are learning is that in these single atom thick derivatives, we can teach old materials new properties, we can control properties by changing the chemistry around them, and we can access new and unique phenomena. Let's look at silicon and germanium. These are the most important materials of our time. They are used in a large range of applications, including modern computing technology and solar cells. This is the crystal structure of germanium. Every black and red atom in this model corresponds to a germanium atom. We developed the synthetic methodology to extract this single layer of germanium atoms. However, in order for this single layer of germanium atoms to be stable, every atom needs to have the same number of bonds as in the original germanium crystal, meaning that we need to terminate the top and the bottom of the layers with a chemical group. We call this material germanane. We have learned how to grow crystals consisting of sheets of germanane that are stacked together. These crystals can be exfoliated down to single layers by fitting them between pieces of tape and stamping them onto substrates where we can then study their electronic properties. Scaling down germanium to a single atom thick, two-dimensional framework gives this material new properties. For instance, germanium does not efficiently absorb or emit light. However, germanane has a different electronic structure, allowing it to absorb and emit light efficiently. This gives germanane great potential for optoelectronic devices, including light-emitting diodes and solar cells. Also, by changing the identity of the chemical group that is bonded to the surface, we can tune where it absorbs and emits light, from visible light to the infrared. Finally, germanane and the tin derivatives have been predicted to exhibit novel electronic phenomena, such as being a two-dimensional topological insulator. This would imply perfect conduction with no resistance along the edges of a single sheet. There is no doubt that shrinking materials down to their chemical limits, to the atomic scale, will take materials that can just barely be seen to a future we can just barely fathom.